Welcome back to our video series on transport techniques and their application to signal and image analysis in machine learning. In this video, we're going to talk about the cumulative distribution transform, which is a new way to represent 1D signals in such a way so as to render data science problems like estimation and classification easier to solve. I'll just make a note that most of the ideas, the materials discussed in this video come from this paper highlighted here below. The Cumulative Distribution Transform and Linear Pattern Classification, published in 2018. So let's begin. Let's define the Cumulative Distribution Transform. Let's begin by assuming we're talking about signals, which are modeled here as functions. S of x, x is the independent variable, s is the dependent variable. So we have two functions here, s of x and s naught of x. For simplicity, for now, we'll assume that these are positive functions and that they both integrate to 1. In other words, they're probability density functions. Now let's look at a map, f of x, that matches their cumulative integrals. In other words, let's imagine that this is our signal s of x, let's say the uniform function between 0 and 1, uniform distribution, and let's say that we pick a coordinate x in the domain of s naught, and we calculate the area under the curve of S naught. Remember, the signal S naught is positive, so we have to be talking about the positive area. And then we find the equivalent spot under the curve of our signal S of x such that the area under S naught and S is the same. So there will be a mapping from the domain of signal S naught to the signal S, which we call f of x. Right? And simply the mapping is the coordinate in the domain of S such that the integral under the area under the curve of S is matched to the area under the curve at x, right? So the way to write this with mathematical notation is that we have an integral over our S naught function, which we'll begin calling our reference signal, and it goes up to certain value x. And then there's an equivalent integral over our signal s of x, but now you have to go up until f of x. Now, if we use the antiderivative notation or the integral notation, where we call capital S naught the integral, the indefinite integral of S naught or a function S naught, right? So we call capital S the antiderivative of S. Then we are talking about finding this relation so that our accumulation or our cumulative distribution evaluated at x for signal S naught, the accumulation of signal S naught, should be equal to the accumulation evaluated at f of x. Right? Now, because we defined our signals to be positive functions, their integrals will be also positive functions, and in addition, they will be monotonic or one-to-one functions, which means we will have such a thing as the inverse of either these cumulations, which will take the inverse of capital S to obtain the map f of x that matches the area under both curves. And this f of x is what we'll call the transform of our signal S. For example, let's take our reference signal to be the uniform distribution between 0 and 1. Then the integral of 1 is x, again within this domain of 0, 1. And if we plug in S naught of x here to be simply x, we define the cumulative distribution transform of our signal S to be the inverse of its cumulative distribution function. With these definitions, for example, taking the reference signal to be the uniform function distribution between 0 and 1, we can now define a forward operation that takes our signal to what we call the transform domain. So we denote the transform domain by a hat function here, which we'll define to be, in this particular case, to be the inverse function of the cumulative distribution of the signal. We can note that this operation is entirely reversible in the sense that we can go from S hat or the transform of S back to signal S. To do that, we once again take the inverse of the inverse, so we obtain the accumulation again, or the cumulative distribution, and simply differentiate the cumulative distribution to obtain our signal S. So here we have a forward formula for the transform and an inverse formula for the transform, and we call this the cumulative distribution transform. And just like the Fourier transform, for example, has a forward formula and an inverse formula, these are the forward and inverse formulas for the cumulative distribution transform. Graphically, this can be understood very simply, very easily. Right? Let's say we have our signal S of x, which again here we're talking about a PDF, in this case a Gaussian, with a certain mean and a certain variance. We're looking to interpret this formula here. So now we first compute the accumulation or the cumulative distribution of this Gaussian function, which is given here, right? And this is our capital S of x. We then compute the inverse of S, which is simply flipping the axis. Whatever was the independent variable before, we now call the dependent variable, and vice versa, right? So basically, to go from the signal to the transform domain, we take the accumulation or the CDF, and then we compute the inverse CDF, which is what we define to be our cumulative distribution transform. So let's define the CDT a little bit more carefully. Again, the CDT is a new invertible and nonlinear signal transform. For us to define the signal transform of signal S of x here, in this case we're plotting a nice smooth Gaussian function, we define it with respect to some chosen reference function or reference signal, which we call S naught of y. In this case, we differentiate here explicitly the domain of the reference signal, which we call y, and x, which is the domain of our signal to be transformed, right? So we can say that x belongs to some domain omega. Omega is the domain of our signal, of where our signal S of x is defined, and omega naught is the domain over which our reference signal S naught of y is defined. And what we do next is then compute the function f from y to x, or from omega naught to omega, right? And this such that the area under these curves are matched, which if we differentiate these two sides here, we obtain essentially the change of variables formula that relates the domain of S naught, which again is omega naught, to the domain of S, which is omega, via the matching of the accumulation function. And once again, we define the transform of S of x to be S hat of y, right? And we chose the variable y to differentiate from the variable x, just the same case that sometimes when you talk about the Fourier transform of a signal f of t, you define f hat of omega, right? Omega and t are different variables here. Y is the variable that belongs to the domain of our reference function, and the map that we obtain is from omega naught, the reference function domain, to our signal domain. And as we just described, an example in the previous slide, a good way to think of this is a forward and inverse map. And the input space is the space of probability density functions, which have a, by definition are smooth, have a density. And the transform space essentially is the set of diffeomorphisms that relate any function from this domain, which is the domain of probability density functions, to the domain of diffeomorphisms, right? Via matching to a chosen fixed reference. Here we fix this reference to be the uniform distribution, although we could have chosen to be any other positive distribution. So once again, we relate this to the ideas of, for example, Fourier transforms. Fourier transforms map uh, uh, absolute integral functions, say L1 space to L1 space or L2 space to L2 space, depending on what you would like to talk about, right? The cumulative distribution transform maps it's a map from the space of probability density functions to the space of diffeomorphisms, and of course, by knowing what the reference was, we can go back from the space of diffeomorphisms back to the space of smooth probability density functions. So let's talk about some properties of the CDT. Specifically here, we're going to derive what we call the composition property. Let's imagine we have a signal S of x. Again, x belongs to some particular domain, omega. And let's imagine we have defined the CDT of the signal S of x, where now S hat of x corresponds to the CDT, but its independent variable we call y, and y belongs to some domain, which is the domain of our reference signal, which we described earlier. So the question right here we are asking ourselves is, what is the CDT of this other function, which we call Sg of x, which is obtained via some kind of change of variables, essentially, of our original signal S of x. Essentially, we compose S with some function g of x times g prime of x, where g is a one-to-one increasing function, which is differentiable, right? So we have defined our signal S of x, the transform of the signal S hat of y, and now we would like to obtain the transform of the signal Sg, and we would like to understand how it relates to the original transform, the signal, the transform of the original signal. So let's start by rewriting the definition of the CDT itself, right? So as we talked about just before, the CDT is a matching of cumulative distributions, essentially, between the given function, the given PDF, and a reference function, which we call S naught, right? So this left-hand side here and this rightmost right-hand side here are basically the definitions from the previous slide. And of course, the definition of the transform of Sg has to also satisfy the same equation, right? So plugging in the formula for Sg, which we defined over here, right? We simply plug in Sg here. And now we perform a change of variables where we call the g of u some function v and g prime of u du to be dv, the standard change of variables. And here we apply the change of variables to the right-hand side over here to obtain the matching between, to obtain a relation between the transform of our original signal and the transform of our modified signal, right? So this means that these values in the integrals have to be the same, so we equate this, and this is true again when the inverse of g is applied to our original transform, right? We're assuming that g here is a one-to-one differentiable function, and so it has an inverse. So in other words, sometimes we'll write just this simple composition here with this composition circle symbol here, which says that the transform of our modified signal S of g is the function g minus 1 applied to the original transform of S, right? And this is the statement here highlighted at the end. So let's look at these properties in some more visual way. So by simply using the property that we just derived, where if we have some kind of modified version of our signal, the transform of the signal is the inverse of the modification applied to the transform of the original signal. For example, if we translate a signal by some value mu here, so here's our original signal and here is S mu, translated by some amount mu along the x-axis. the CDT is composed by performing the CDF operation first and then inverting the CDF. So you can see that in the inverse domain, what happens to the transform, in transform domain, what happens to the transform of the original function is it gets pushed up, right? Here it was pushed to the right. Now in transform domain, it gets pushed up by addition of the mu instead. This is again derived by simply plugging in this translation into the composition formulas. Likewise, we can derive what we call the scaling property of the CDT. Let's imagine that S of SA here now stands for some kind of scaling of our original signal S, right? So if we have our original signal over here in the solid blue curve, the scaled version of the signal is here in the dotted curve. Again, we perform the CDF computation and we invert it, and here you go. And the operation is once again the inverse of A of X, right? So the inverse is 1 over A and applied to our original CDT. And here is our original function, our original composition property, right? And the thing to note here is that whatever happens to the signal, let's say we're performing translation along the x-axis or some kind of dilation here, we're pushing some signal to the left and some signal to the right, or some kind of modification more generally expressed as a composition of the signal. And this modification is essentially borrowing the partial differential equation nomenclature is Lagrangian in nature. It pushes particles along the coordinates of the independent variable, right? This is the modification in original signal domain. This becomes an Eulerian modification in that now they essentially become amplitude modulations in transform domain. We now go ahead and consider the data geometry generated by applying certain Lagrangian deformations to our signal in signal space and look at what this geometry looks like in transform space. For example, if we take a signal S of X here and consider the set of signals that are composed by our original signal plus all of its translated versions, right? We can see that this set is non-convex in the sense that we can take two elements of this set and take their convex combination. That does not yield an element of the set, right? Another way of saying this is the linear convex combination of two Gaussian functions that are translated with respect to each other does not yield a Gaussian function. So therefore, if we take the set of functions here, which once again, in theory, these are functions in infinite dimensional space, but we can sample them and then we can essentially perform PCA, principal component analysis, on all of these translated signals, and we look at the three main components, the three first principal components, we'll see that the set does indeed form a nonlinear space in this reduced PCA space. Now, if we look at the set of signals, the same set of signals in CDT space or transform space, we can see from the derivation we just did that now this becomes a perfectly convex space, a perfectly linear space, and this is reflected in the fact that now the three-component PCA reconstruction of the data set gives you essentially a straight line. This leads us to consider what we call a transport-based generative model for signal classes. Let's suppose we have a class which we call class P here, and let's imagine that this class P is a class of signals that are made up via the composition of a given template, right? Maybe this template in a real situation may be unknown, but we'll imagine that there exists a template which we call P naught. And now that these signals inside class P here are observed under the presence of what we call some confound, right? Some function G that belongs to perhaps some C, some class of function C. Perhaps in this example we'll use G being some kind of translation, with mu here perhaps some random translation parameter. And so this class of P now is a set, an infinite set of signals composed by these translated versions of what we call P naught. Right? So this is the mathematical notation of the set P. The elements of the set, which we call PG here, are given by the composition of this randomly sampled, perhaps G function, which in this case example here we're using simple translations. Similarly, let's consider a class which we call class Q, where now this class Q is made of a second template, which we call Q naught. Right? And again, the set of all possible translates of Q naught is what we call the set Q. And the same mathematical notation is being used here to define the set Q. As we just saw, if we consider the geometry of these sets, they are non-convex, non-linear. So perhaps if we're looking at the problem of classifying these two classes, right, as you can see here from this plot here, in this case you will need a highly nonlinear classifier to do a good job, right? This is the situation if you consider the signal space. Now, as we just saw, if we look at the data in transport space, this data, the geometry of this data is perfectly convex and it can be modeled in fact as linear subspaces. And in this situation, one can take of numerous classifiers which would do a good job. A basic classifier here being the linear discriminant analysis, perhaps, or linear SVM, or even perhaps just the mean of this data set here, projection over the difference of means will also do a good job. So if we now go ahead and try to set up some classification example for these three signal classes, for three signal classes, they are generated by, a template which has essentially a Gaussian signal, another template which has a two-bump signal or a convex combination of two Gaussian signals, and another template yet, a third class, which has a combination of three Gaussians, right? And let's imagine that we observe all of these functions under some random translation, right? And if we try to perform linear discriminant analysis, Fisher linear discriminant analysis in signal space by first taking a bunch of training data and fitting the model and then projecting test data onto this trained model, you will see that the performance of this linear classifier will be very, very poor, essentially because these classes in signal space do not form convex sets, and therefore they cannot, strictly speaking, be linearly separated. In transform space, as we just saw, any signal in transport space can be, transform space can be composed of a linear combination of two other signals of the same class in transform space. And therefore, if we repeat the same procedure, that is take a bunch of training data, fit the linear model in this training data, and then project test data onto the same model, now we get perfect separation. So now we can summarize this discussion about convexity and linear separation in what we call the linear separation theorem, where we consider two classes of signals, capital P and capital Q here, where the P and Q are defined, the elements of P and Q are defined via composition of some randomly sampled confound functions, which will belong to some kind of set of one-to-one functions, which we call C here. And of course, we postulate, we pose the problem as a non-overlapping problem, meaning there is no element, there is no signal that will be an element of both P and Q simultaneously, right? So the intersection of these sets is empty. Then, from what we just saw, we can postulate that these signals, these classes in transform space, in CDT space, will be linearly separable if and only if the class of confounds in its inverse form is convex. So, which means if I can take the linear combination of inverse functions of the inverse of functions g and yield another function which is also in the set of inverse functions, then these two sets will be convex and therefore linearly separable. And one thing to note is that this will be true for any reference S0 that we choose to define the CDT to begin with. In addition, this does not require knowledge, does not require us knowing what the actual templates for the two classes are. So it's a very convenient result, which is summarized in this plot here, where the class P here are elements, signal elements here. In this case, we're using the translation example we just showed, the class Q, and you can see these are nonlinear, non-convex sets, which in transform space become perfectly convex. Right? You can see these publications for different versions of this theorem, and basically the gist of how to see this is to just look at the definition of these sets in transform space using this composition property that we just derived. Right? This is the composition. So obviously, if the set C minus 1 here, which is the set of inverse functions of our confound, is convex, then this entire set P will be convex as well, and by the Hahn-Banach linear separation theorem, these two classes will be linearly separable, and you can generalize this for n classes as well. And so there you have it. So in summary, in this video we defined a new signal transform, which we call the cumulative distribution transform. We defined it for positive signals which can be interpreted as PDFs, so probability density functions. Like the Fourier transform, this is an invertible transformation, or in other words, it's a way to represent your signals. It has mathematical properties, just like the Fourier transform has translation, dilation properties, etc. This has a composition property, which also can be formulated as translation and dilation specifically. And we also discussed a convexity and linear classification theorem. And this picture summarizes this linear classification theorem. For further reading, I recommend the original paper, which defines this cumulative distribution transform, as well as certain extensions and applications of this transform for parametric signal estimation problems. In this third paper here, we extended the definition of this transform to now signals that are arbitrary, meaning they can be signed signals of arbitrary magnitude, right? As you remember from this discussion here, the cumulative distribution transform, as discussed here, is defined only for positive PDFs. This paper extends this for any kind of signals, essentially. And I also encourage you to look at this preprint, which applies, combines this new signal transform together with near subspace type methods for high accuracy end-to-end signal classification.